episode of 3-minute videos with Nathaniel, and today we will now do question 1I of MAT Oxford 2010. This question is phrased like this. However, although this might seem like a gnarly integration problem to you, actually it's just a matter of drawing the graph. This essentially means that the area, the gradient of the area is 0 when A is this. In other words, when is the area a maximum? Well, you can just look at the graph. The graph of 4 minus 2 to the power of x squared looks like this. However, this graph may look like 4 minus x squared, but keep in mind that x squared and 2 to the power of x squared are two completely different functions. Why? Because I have organized all polynomial, exponential, and heteronomial functions, whatever that is, into a faster growing hierarchy. So it starts with 1, then it's less growing than x, less than x squared, less than x cubed, less than less than 2 to the power of x, 3 to the power of x, less than less than 2 to the power of x squared. So you can see x squared is much slower growing than 2 to the power of x squared. Understood? This actually means that 2 to the power of x squared grows faster than any polynomial or linear exponential function in x. Now, let us work out when is the area a maximum. Keep in mind that the area under this area is actually a negative area. So, when is the area a maximum? I'll give you some time to figure this out. Yeah, right, it's at the intercept. So, the intercept. So, 4 minus 2 to the power of x squared equals to 0. Now we solve for x. Now, you know, x squared, this actually can be written as log 4 equals to 2. X is root 2, or the minus square root of 2, but since our minus square root 2 here is negative, and since a, our little a here, is actually very much positive, x is the square root of 2. Now, this also means that our a here is the square root of 2, because this basically means that the area is a maximum when a is the square root of 2. Does that make sense here? Well, obviously it does, because this gnarly integration problem, you don't have to do any integration. You just have to look at the graph, decide which functions are faster growing, then solve for x. See? Simple as pie, without having to know how to integrate this gnarly thing here, which I don't even know how to integrate myself. But we can use some several analytic methods, one of which is this. Now, this video is the 95th video. Let me give you some facts about 95. 95 is the third of a triplet of semi-primes. So 93 is 3 times 31, 94 is 2 times 47, 95 is 5 times 19. So I'm not going to prove it to you, but every triplet of semi-primes, one has to be divisible by 2, one divisible by 3, and another divisible by 5. Make sense? Well, it does. 95 also has a handy representation. See here? The 5 is the exponent. Now, let's generalize this to 3 times 2 to the power of n minus 1. When this number is prime, it's called a subic prime. Let me write that down for you. But unfortunately, when we substitute 5 into this equation, our little 95 here isn't prime, so 5 won't work. Other exponents that do work are 1, 2, 3, 4, 6, and 7. I memorized the first few exponents because I love subic primes. No, really. Sounds interesting, right? Well, I wish I could continue talking with you about this function, and since this function is so cool, why don't you try other area problems for yourself? Just use the methods that's taught here. Or, if you want to check when a function is easily integrable, like in this 4 minus 2 to the power of x squared was replaced instead with a 4 minus x squared, then you could easily check the area at that point and see it's a maximum. Then you could plus minus some small number like 0.001 to check your answer. Bingo! Now you have a technique for finding areas and some little facts about 95 since it's the 95th video, so why not celebrate? Anyway, we got 5 more videos to reach 100 or 10 squared, or as I like to call it, a Hackett videos. Actually, I like that name. Well, anyways, thank you and goodbye.